I'm recording a video to go over the in-class problems that we worked yesterday. That would be, I guess, Wednesday the 30th in class. A lot of people seem to have some problems with how to do them, and so I wanted to work through that so that you would get an idea of what we're supposed to be doing. So you should be able to see my screen right now. It's kind of weird seeing myself on the video, so I apologize about that, but you can at least know I'm talking to you. So let's just kind of start off. One of the first things that when you're working a problem like this, you want to get an idea of kind of what you're dealing with, what the situation is. And so that's why I always will put kind of this little thing at the top here to really get an idea of, well, this is kind of where we are. This is what the situation is. And so we know that we're running a regression, but it helps to know kind of what we're actually doing. So in this case, the dependent variable for the regression is a student's final grade in the class. And it's important to note that this is in decimal form. So 0.85 would be like an 85%, okay? Because that's important to how we interpret the coefficients later on. Another thing that we see is that attendance is measured in days. So that, notice I basically list out how each variable is measured because those variables are then listed down here at the bottom. So there's basically two places you can get a list of the variables usually. One is in the actual regression output. So there's the 4 variables that we care about. And then we can know how to interpret those variables based on their units up here. So we know attendance is measured in days. The 2 GPAs are measured in GPA points, which makes sense. And ACT scores are measured in its points. Okay, so I give that up there to give you some context on how to interpret things. So now moving forward, I give you a basic regression output from Excel, and I give you some questions. So this is exactly how the test is going to be laid out. We're going to be doing the exact same things, and so I want you to take a minute to kind of familiarize yourself, and you should already be familiar with kind of the layout of this structure. So again, you've got the basic regression statistics here at the top, things like your multiple R and your R squared. You've got your ANOVA table here in the center, which you're going to be filling out in part 2. And then you've got your coefficients and their statistics here at the bottom. So in fact, I set to fill in the blanks of the chart as part 2. I'm going to go ahead and do that first, because I think that's, it's fairly important to go ahead and knock that out, and that'll help us answer some of the questions in parts 1 and 3. So let's go ahead and do that. So one of the easiest things to fill out once you get to this part, the first thing is going to be this column here, the degrees of freedom column. Because you can really do that without too much else. One of the things that you need to know to be able to do that is you have your observations here. That's your N, that's your sample size. From that, then you should be able to fill in everything else. So if you remember from our notes in class, this first cell here, the degrees of freedom of the regression, that's K. And if you don't remember what K is the number of independent variables. Now there's two places you can find the number of independent variables. One, they'll usually be listed in this paragraph here at the top. And then the more accurate and easiest place to find it will be listed here in the right next to their coefficients. Now I will point out the intercept is not one of our independent variables. That's our beta 0, or in this case is our B0. And these are our actual independent variables. We have 4 independent variables in this case, so K is equal to 4. So we can put here that our regression degrees of freedom is just 4. Now, for our residual degrees of freedom is N minus K minus 1. So N minus K minus 1, N is 50, K is 4. So 50 minus 4 minus 1, that's 50 minus 5. So our residual degrees of freedom is 45, right? And finally, 2 ways to get the total degrees of freedom. One, it's just N minus 1. So N minus 1, 50 minus 1 is 49. The other way is you can add up the 2 above it, and both of those answers will give you 49. So we get 49 total degrees of freedom. Now we need to move on over here to filling out this next part of the table. So usually the next thing I would try to do is try to fill out the sum of squareds column. And notice we already have our sum of squared of the regression. So our SSR is already filled in. So we can use that to figure out the other two. Now, so one of the things to do is, again, this is like kind of a puzzle. You have to say, okay, what information do I know? What information am I trying to get? So one thing to basically think about is, okay, let's kind of look at some of the formulas that we know to kind of get to these other things. Excuse me, I'm yawning here. I'm going to open up Paint here just to give it. So we basically have two formulas that we might really care about to get to those. One is going to be our R squared formula. I can't. R squared. It's hard doing this with the mouse. R squared is equal to SSR divided by SST. Okay, so that's one formula that brings together some of those things that we want to find out. The other formula that we're going to use in a minute is going to be, we know that the sum of SSR and SSE, so SSR plus SSE, this one would be really nice to have like a touch screen computer or something. SSR plus SSE is going to equal SST. Okay, so we can use these two formulas to kind of help us fill in that other part. Now, we can't use this second formula yet, the SSR plus SSE equals SST. We can't use that yet because we don't have we have SSR, but we don't have SSE or SST, so we can't use that yet. Three things in the equation, we only know one of them, that's not much help. However, this top one, there's three things in this equation, SSR, SST, and R squared. And if we come back over here to our document, we see we actually have two of those three things. We have SSR here. We also have R squared here at the top. Okay, so we can use that information then to solve for SST. So let me come back to Paint. So we're going to plug into this equation. Now I've forgotten what our numbers are. So I'm going to round to say 4 decimal places. So a lot of people in class were asking me yesterday, how many decimal places do I need to round to? The more the better. But, 4 in this case is probably pretty good. So we'll go with that. So our R squared is 0.3286. Okay, so let's go back to our Paint. So we get 0.328. Ooh, that's a terrible 8.6. And that's equal to SSR, which we know, come back over here, SSR is 3.0937. 3.0937 divided by SST. Now we can solve this equation for SST. Essentially, you multiply both sides by SST, which gives us, so this goes away. This is times SST. Okay, then you're going to divide both sides by the 0.3286. So we get the 0.3286 over here. And so we end up with SST, so this goes away. SST is equal to 3.0937 divided by 0.3286. Let's grab a calculator. Got a calculator here. So 3.0937 divided by 0.3286, we get 0.94, let's say 0.94148. So 9.4148. So let's go back over there. So 9.4148. And depending on how many decimals you take this out to, you might get a slightly different answer than that, but that's pretty darn close. Now that we have this, we can use this information and this second formula here to figure out our SSE, because we know SSR, we know SST. We know the sum of these two have to give us our SST. So to find our SSE, it's just as simple to come and do a quick subtraction. So the number we just got there, minus 3.0937 3, I was going to do this 6671. You only get 6.3211. So 6.3211, and that is our SSE. Now that we have that, we can fill out the rest of the chart pretty easily. Your MSR is just your SSR divided by K, so 3.09366671 divided by 4. Use our calculator to do that. 3.09366671 divided by 4. 0.7734. 7734. Okay. Now I want to do residual. Our MSE. That's the mean squared error. That is our SSE divided by 45. N minus K minus 1. So we come here and do 6.3211 divided by 45, and we get 0.1405. Whoops. Okay. Now our F statistic is our MSR divided by our MSE. So 0.7734 divided by 0.1405. Come here and do that real quick. 0.7734 divided by 0.1405. And you get a F statistic of 5.505. We'll go with that, 5.505. Now, significance of F, this is basically the p-value of the F statistic. So we need to use the F table to get that. So we're going to go pull up an F table. Let's see if I have one pulled up here. I don't. So let's just, hey, look, there's YouTube. Let's go out to D2L. We'll go into our class here. Now, there's plenty of F tables available out on the internet. You can just Google, but I have these pulled up, and this will be the one that you'll have on the exam. And so you probably want to get used to using this particular F table. So let me open this up. Okay, so here's our F table. Okay, so to remind you how to use an F table, essentially, we've got at the top our numerator degrees of freedom. Okay, along the left-hand side here, we have our denominator degrees of freedom. Your numerator degrees of freedom is going to be K, so in this case, it's 4. Your denominator degrees of freedom is going to be N minus K minus 1, so in this case, 45. So we'll go to the fourth column, go down to row 45, all the way down. Now, this particular table does not have a row 45, and so what we need to do is we need to decide, okay, we're going to use 50 or 40. My general rule is to always use the smaller, right? Unless you're like really close to the next one, right? But it's always a conservative viewpoint to take the smaller of the two. So we're going to go with the 40. And so we go to our fourth column here. And so we're really looking at these 4 numbers here. Let me zoom in a little bit so you can see it a little better. We're looking at these 4 numbers in column 4. So the 2.09 down to the 3.83. Those are after that we can ignore every other column and every other number pretty much in the F table because we're just looking at those 4 numbers. Basically, well, I can't highlight them, but these 4 numbers right here, the 2.09, 2.61, 3.13, and 3.83. Now we need to go back and look and say, okay, what was our F statistic? So coming back to our F statistic was 5.505. So we come back to our F table and we say, okay, in those 4 numbers that we care about, where does 5.505 land? Well, notice, okay, it's 5.05 would be down here in the table right below the 3.83, right? Because the numbers are getting bigger as you go down in the table. So 5.05 would be in this area here right below this 3.83. So it'd be right below the 3.83. So then what we do is we come all the way over here to the left-hand side of that row, and we see here's our p-values, okay? And since 5.505 is right below the 3.83, we know that our p-value is below 0.01, okay? So we know that our p-value is less than 0.01. So then on our table, coming back to our table, we would just write the significance of f is less than 0.01. Okay, because it's a very small p-value there. All right, so that's filling in this whole ANOVA table here. Let's jump down to the next one and let's fill in this regression output kind of table here. Now, the way to fill in the first three here is just to remember, let me come back to my paint. We have a basic formula for this, and we have that the t-statistic is equal to our coefficient, which is our little b, divided by the standard error of that little b. Okay, that's basically our t-statistic here, because the hypothesis that Excel is testing is, if it's equal to or not equal to 0. And so if that's the hypothesis you're testing, this is the formula for your t-statistic. So using this formula, there's three things in the formula. If you have two of them, you can always solve for the other one. Excuse me, yawning again. Oh, okay. So here we are. So we're back to our Word document. So we know essentially that our t-statistic, this third column here, is equal to our coefficient divided by our standard error. So first column divided by second column should equal our third column. Okay, and if you actually test this first row, you can see that 0.335 divided by 0.0335 gives us 9.977, etc. Okay, so you would get that t-statistic there. So probably the easiest one of these to calculate is actually this third one here, because we just need to do this coefficient divided by the standard error will give us the t-statistic. So very straightforward. I'll go ahead and do that. And the sign is important here, so we need to remember we're doing a negative number divided by a positive number. So our t-statistic will be negative. Okay, and so let's go ahead and do that. So 0.00056,251 divided by 0.00955,946. Oops, 946. And so our t-statistic here is negative. Again, it's negative because it's a negative divided by a positive. Negative 0.0588. So I'll put that here. Negative 0.0588. Okay, so there is that t-statistic. Now these up here, not really any harder. Okay, to get the coefficient, basically coming back to our formula down here. Get sleep, guys, it helps. Okay, so the formula down here at the bottom, to get the the coefficient by itself, you need to multiply the t-statistic by the standard error, so we'll come over here and do that. So to get to the coefficient, we basically multiply our standard error times our t-statistic. So again, it's going to be negative, because we have negative times a positive. So we come here to our calculator, and we do 2.878832.159 times 0.00977. And so we get a coefficient of 0.026. We'll go with that. 0.026. Whoops. So that's our coefficient there. It's actually 0. We'll say 0.2. Okay, or 0.3, I guess. We're really rounding there. Okay, and then the last thing you figure out is the standard error. Again, to calculate that standard error, if you rearrange the formula here, solve for standard error, doing a little algebra, you'll see that the standard error is going to be equal to our coefficient divided by the t-statistic. So we need to do that to calculate our standard error. So coefficient divided by t-statistic. So we'll come here and do that. So coefficient is 0.08429. We'll go there, divided by the t-statistic, which is 11.31436.732, and you get a standard error of 0.00745. That's correct. Yeah, okay. And then finally, to get the p-value here at the end, to get p-values, you always have to go out to the table to look them up. So to get this particular p-value, you need to go out to the t-table. Why is the t-table, not the f-table? Because this is a t-statistic that we're looking at. So we're finding the p-value of that t-statistic. So let's go out, come back over here to our D2L. We'll go back to our handouts. We'll get our t-table. Pull that up real quick. Okay, so here's our t-table. We're going to use it the same way that we've always used a t-table. Okay, we need to know our degrees of freedom. On a t-table, your degrees of freedom is n minus k minus 1, which in this example is 45. So we'll come down to row 45. Okay, here's row 45. We have a t-statistic of, let's remind ourselves because I've forgotten. Let's see, 2.03. So we come here and look, okay, where would, in this row 45, where would 2.03 fall? And it would be between these two. It's bigger than 2.01, but smaller than 2.4. So 2.03 is right here between these two. So we need to come all the way up to the top. And so that means the area in the upper tail is between 2.5% and 1%. So somewhere in between those two numbers. Now, Excel is always running checking a two-tail hypothesis. So if we're checking against a two-tail hypothesis, that means we have to double that area to get our p-value. So when we double that area, so 0.01 doubled is 0.02. 0.025 doubled is 0.05. So our actual p-value is between 2% and 5%. So we come back to our table over here and come back to over here. And so our p-value is between 2% and 5%. There's a lot of different ways you can write that. I'm just going to say it's 2% is less than p, which is less than 5%. But even if you just wrote between 2% and 5%, I'm happy with that. Okay. All right. Now with that, now we've got our whole table filled out. We can go down here and answer the questions as we need to answer them. Okay, so we're going to write out the model. The model is essentially our population regression equation. Since we're in Word here, it's a little hard to do, so I'm going to use Word's equation editor here to do that. But when you're doing it on the test, obviously you'll just do that by hand. So your population regression equation is your y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 on and on and on plus epsilon. Except in this case, instead of putting y's and x's, we're actually going to fill in the names of our variables. So remember, your y is your dependent variable. And so the dependent variable in this case, coming from up here at the top, the dependent variable is student final grade. So we're going to say your y is the final grade is equal to beta 0 plus beta 1. Then our x variable, and our first x variable is a 10, so we'll write a 10 there, plus beta 2 times term GPA plus beta 3 times prior GPA plus beta 4 times ACT plus epsilon. Okay, so that there is your model that's being estimated with the output. Okay, so that is kind of your population regression equation. Also, we usually refer to that as our model. All right, so part B. Explain the estimated coefficient of the ACT variable. Let's stop there. Let's just do that part first. So the estimated coefficient of the ACT variable is found under the coefficient column and then in the row for the ACT variable. So that is that 0.007211065 number. Okay. So we need to explain what does that number actually mean. And so it helps to remember, and this is what I was talking about in class yesterday, it helps to think about that number as a slope. Okay, if you remember how we interpret slopes, the slope is the change in y with a 1 unit change in x. Okay, so when we estimate, so when we're trying to interpret a coefficient, that's usually the way that we'll talk about it, is it's the change in y with a 1 unit change in x, holding everything else constant. Okay, so the way to, the interpretation would be if a student's ACT score increased by 1, then the final grade of that student would increase by 0.007 to 11065 points. Points on average. And remember, this is an average effect, so it's kind of important to say that we're not saying that every student who gets an ACT score 1 higher is going to get this increase, but we're seeing that that's an average change across the sample. Okay, so that right there, that is the effect of just a 1 unit increase. Okay, the next part of the question says, okay, well, what if it's a 5 unit increase? Well, so if a student's ACT score increased by 5, then the final grade of that student would increase by, and in this case, if the change in x is 5, then the change in y is going to be 5 times this slope. So we'll come down here and we'll do that. So 0.007 to 11065 times 5. So it's 0.036. So it would increase by 0.036 points. And again, the way to interpret that, this is really basically 3.6 percentage points, right? Because the way that we know that, coming back over to the top, our final grade is in decimal form. So this right here, this is a change of 3.6 percentage points. And so that's helpful to remember. All right, part C, write out the hypotheses to test. Let's see, I'm going to bring this up. Write out the hypotheses to test if there's a relationship between ACT score and the final grade in the class. Again, I'm going to use Word's equation editor so that we can easily do that and see it in the right way, since I can't write directly on here. But again, on the test, you'll just do this by hand. So HO, let's see, HO is, and this, because this is ACT, that's the 4th beta, so we're really testing an equation, a hypothesis about beta 4 here. So HO is that beta 4 is equal to 0. And HA is going to be that beta 4 is not equal to 0. So again, these hypotheses are testing to see is there a relationship or not. The null hypothesis, that beta 4 equals 0, is saying there's not a relationship between ACT scores and your final grade in the class. Because if that slope was 0, then it doesn't matter what your ACT score is. It doesn't impact your Y. Our HA, our alternative hypothesis, is saying that beta 4 is not equal to 0. We're not saying what it is. We're just saying it's not 0, which means there is a relationship between ACT and the final grade. Okay, so that's your hypotheses. And then part D here is the ACT variable significantly related to the final score? So we come up here to our ACT variable to test that hypothesis. Basically, part D is saying now test these hypotheses. So to test that hypothesis, we need to come up here and look at the p-value for the ACT variable. The p-value is between 2% and 5%. So if you remember how to test a hypothesis, when you're testing a hypothesis, you want your p-value to enable to reject the null of the hypothesis. You need to have your p-value less than your level of significance. Now, I didn't give you a level of significance here, so you could choose one. So the 3 levels of significance that we're usually dealing with are 1%, 5%, and 10%. So if you chose 5% or 10%, okay, so I'm going to say, come here and say if alpha equals 5% or 10%, then ACT is significantly related. It's spelled significantly related to final score. And why is that? Because our p-value is less than 5%. Okay, so our p-value being less than 5%, then if our alpha is 5% or 10%, our p-value is less than our alpha, which means we reject the null. And if we reject the null, that means we're saying that there is a relationship between ACT and the final score. Now, if you picked an alpha of 1%, then ACT, we'll say then there's no evidence that ACT is related to the final score, right? Because in this case, alpha would be less than our p-value, because we know our p-value, again, somewhere between 2 and 5%. We don't know it exactly, but we know it's between 2 and 5%. So if we know our p-value is between 2 and 5%, our alpha is 1%, so our p-value is bigger than our alpha, which means we failed to reject the null, which means we didn't find any evidence that ACT is related to the final score. So that's how you work that one. Part 2 was filling in the blanks. We already did that. Question 3, write out the full hypotheses being tested by the F statistic. So again, the F statistic is what we calculated up here. That's this number here. Okay, so we want to write out those full hypotheses. Now the hypotheses for an F statistic is it's a joint hypothesis test, and so what we're going to do is we're going to write out the full hypotheses. So HO, remember the null hypothesis for the F test is that nothing in the equation matters. None of the variables are related to our dependent variable. So in this case, it would be that beta 1 is equal to 0, and beta 2 is equal to 0, and beta 3 is equal to 0, and beta 4 is equal to 0. Okay, that is our null hypothesis. Right? Our alternative hypothesis, HA, is a couple ways to write this, but I'm just going to say at least 1 beta is not equal to 0. Okay, so our alternative hypothesis is that at least one of those 4 beta coefficients are not equal to 0 in the population. Okay, so what is the p-value of the F statistic? Well, we already found that. We come up here, we found our significance level, it's less than 1%. So we come here, what is the p-value? It's less than, so p-value is less than 1%. So then what's our conclusion? Okay, well, again, whenever you're trying to say, what's our conclusion from a hypothesis test, we need to know what our level of significance is. Well, in this case, whether it was a 10%, 5%, or 1%, our p-value is less than all of those. Okay, so our p-value is less than 1, 5, and 10%. So, no matter if alpha is 1% or 5% or 10%, we would reject the null. And so there's at least one significant relationship in the regression equation. Okay. And that's it. And so we basically were rejecting the null here. So they're not all 0. At least 1 beta is not 0, which means at least something. We don't know what from the F test, but at least something is significantly related to our dependent variable, which is the final grade. Okay, and that's it. That is all three pieces of this. So question one is basically making sure you know how to interpret a coefficient and how to tell if a coefficient is significant or not by using its p-value. Okay. Part two, question two, is making sure you can fill in all the blanks on the chart. Question three is making sure you understand how to use the F statistic of the regression and use that to test the hypotheses that basically nothing is significant, so there's no relationship, or that something is significant, and that's that part. So fairly straightforward, right? I think we're in at 35 minutes now, but that's because I'm pretty long-winded. You should be able to do this fairly quickly. If you have any questions, again, feel free to call me at my phone, shoot me an email, shoot me a text message, whatever. Remember, your test is on Monday, and so if you have any questions, let me know. Otherwise, good luck, and I'll see you on Monday.